To process data on a global scale, engineers rely on sprawling clusters of commodity hardware to distribute the workload. The initial solution to this coordination problem was MapReduce. It provided a framework for engineers to run massive computations across thousands of nodes without manually managing the distribution of tasks. But MapReduce relies on a specific safety mechanism. Between every computation job, the system must write all intermediate data to an external, stable storage system like a physical hard drive. This architecture is inefficient for iterative machine learning algorithms like logistic regression or PageRank. These models require dozens of sequential passes over the same dataset to reach an accurate result. Forcing the system to physically write and then read that data from a disk on every single loop turns a computation task into a massive waiting game for disk I/O. This is the standard Hadoop loop. First, the system computes the data, serializes it into binary, and writes it to a physical disk. To protect against data loss, that newly written file is then replicated across the network to multiple other nodes in the cluster. To start the next iteration, the system must read that data back off the hard drive and deserialize it back into usable Java objects. Storing that intermediate data directly in volatile RAM removes the disk and network steps from the cycle entirely. While in-memory storage is the obvious solution to latency, it introduces a severe architectural risk. RAM is volatile. If a single machine loses power or crashes, the memory is wiped and the entire multi-hour computation is corrupted. In large clusters, individual nodes fail frequently. Any system relying on RAM must recover data without restarting the entire job. The traditional approach for keeping shared state in RAM across a cluster is distributed shared memory, or DSM. DSM systems operate on fine-grained updates. They allow applications to read and write to any individual cell in a large table at any time. Because any cell can change at any moment, the only way to provide fault tolerance is to constantly copy the entire state across the network, or log every single microscopic edit. For data-intensive workloads, this logging process floods the network bandwidth, creating a new bottleneck that negates the speed of the RAM. To make in-memory big data viable, engineers had to move away from the ability to edit individual pieces of data. Spark's solution is the Resilient Distributed Dataset, or RDD. This is a read-only collection of records partitioned across the cluster. RDDs are immutable. They can only be created through coarse-grained transformations, operations like map, filter, or join that apply the same mathematical function to an entire batch of data at once. This restriction allows for a new form of fault tolerance. Because the dataset is built through bulk operations, Spark doesn't copy the actual data. Instead, it logs the sequence of transformations used to build the dataset, a record called its lineage. If a node crashes and a partition of memory is lost, Spark looks at the lineage graph and reruns the specific transformation on the original data to rebuild only what was lost. By trading individual edits for lineage logging, Spark achieves fault tolerance without the need for constant network replication. This lineage graph doesn't just provide safety, it dictates how the system physically schedules tasks across the cluster. Spark distinguishes between two dependencies. In a narrow dependency, each parent partition is used by at most one child partition. This allows a single node to execute an entire pipeline of operations locally without any network communication. In contrast, wide dependencies occur during operations like a join. These force the system to pull data from multiple parent partitions, requiring a shuffle of data across the network. Spark's scheduler analyzes the lineage graph to group as many narrow transformations as possible into a single stage, delaying the expensive network shuffle until it is absolutely necessary. This also makes recovery faster. Lost partitions in a narrow stage can be recomputed in parallel on different nodes without stopping the rest of the cluster. By categorizing these dependencies, Spark minimizes network traffic while ensuring that localized failures remain localized. Even with an incredibly efficient architecture, a massive dataset may eventually exceed the physical RAM available across the entire cluster. Spark manages this through a least recently used eviction policy. When memory is full, the system degrades gracefully, pushing the oldest RDD partitions back to the physical disk to make room for new data. Unlike traditional DSM systems that can suffer extreme performance degradation or crashes when memory is exhausted, RDDs act as a reliable fallback. They provide volatile RAM speeds when space allows, but fall back to disk-level reliability when resources are stretched, ensuring the computation continues. This data compares the performance of Hadoop against Spark during a logistic regression task on a 100-gigabyte dataset. In the first iteration, both systems operate at similar speeds. At this stage, both frameworks are limited by the physics of pulling raw data off the hard drives for the first time. But in subsequent iterations, Spark's processing time drops dramatically. On a 100-node cluster, Spark performs over 20 times faster than Hadoop. This speedup is the direct result of the RDD architecture. Keeping intermediate results in RAM as Java objects bypasses the disk I/O and serialization overhead on every pass after the first. MapReduce was built for a different era of data processing, one where data was read once and never revisited. As machine learning became more iterative, the industry needed a way to leverage distributed memory without sacrificing the reliability of a cluster. Trading fine-grained data manipulation for coarse-grained lineage logging allowed the system to scale without the overhead of constant replication. Resilient distributed datasets enabled interactive, multi-pass machine learning at a global scale.